Hey, ninth graders, we are continuing today with looking at graphs. So this whole unit is about it's called functions and their graphs. So we're talking about what makes a function. We're talking about putting functions onto graphs and how to interpret them and how to evaluate them and how to talk about them in a mathy way. So right now, so far, we've just been kind of building up a foundation for all of our things that we want to talk about. And so this is one of the major ideas that we want to talk about. And now we kind of have some vocab and some ideas that we can go along with to be able to really fully talk about some of these main ideas. This is one of those ideas that will stick with you and continue to pop up in years to come. If you're somebody who saves your notes from year to year and puts them in little folders and keeps them in your closet or something, this might be one that you have some sort of sticky note on and say I'm going to be coming back to this, because you will be coming back to this in 10th grade. I guarantee it. I think at the very beginning of the school year, you'll be coming back to this in either 11th or 12th grade, depending on how your IB teacher builds up your progress through the years. But this is definitely something that continues to pop up. So we have functions that are even and odd. Not only can numbers be even and odd, functions can be even and odd too. And the first thing that I want to tell you is that the way that you interpret numbers to be even and odd will also be helpful for you to determine whether a function is even or odd. So keep that in mind as we're going through this lesson about how can you use what you know about even and odd numbers to talk about even and odd functions. First of all, what does an even function look like? An even function is a function that has reflective symmetry. Remembering all the way back to one whole year ago when you were with Miss Terabelli and talking about all of your transformations, you have objects that have symmetry about your transformations. So when you have something that's symmetric across a reflective symmetry, means that they're reflective across some sort of axis of symmetry. There's this line that goes down. We talked about parabolas being reflective across an axis of symmetry. And this one is an example. Even functions are an example of something that has reflective symmetry, specifically reflective symmetry across the y-axis. It's not just any reflective symmetry. It has to be a very specific type of reflective symmetry across the y-axis. Some examples of things that are reflective across the y-axis are a parabola. Not every parabola, though, is reflective across the y-axis. So you have to keep that in mind. It's only very specific types of parabolas. An absolute value function, which you can see right here, has similar behaviors of a quadratic, of a parabola, but just a little bit more linear. And then we can have functions that look like this. It looks like it stops here, like it doesn't continue up or continue making those waves. So it's unclear whether this is a trigonometric function or whether this is potentially a function with degree 4, or a quartic, as we call them. But these are all symmetric across the y-axis. We have an official definition. A function is even if and only if, remembering back to what we know about these if and only if statements, them being two-way streets. If the first part is true, then the second part is true. If the second part is true, then the first part is true. Symmetric. A function is even if and only if f of x equals f of negative x. So what that means is that if you have a point x, y, if you plug in negative x into the function, it will also give you back y. This is like the how-to of determining functions being even algebraically. So go ahead and just make some sort of note of this is like a set of instructions or like a formula that you can maybe follow of how to determine whether something is even algebraically. So a recap of what we know about even functions so far. It's reflective. It's reflective over the y-axis. It means that when you have f of x, if you plug in negative x into that exact same function, it will give you back the exact same original function as what you originally had. And then you've got these set of steps to follow. An odd function is a function that has rotational symmetry. So rotational symmetry is when you rotate an object and it goes back onto itself. It relapses on over itself, so it looks as if it hasn't moved at all. And rotational symmetry cannot be 360 degrees, because if you think about it, if you rotate anything 360 degrees, it will always map back onto itself. So this is something that has rotational symmetry. It means that it's rotational and symmetric on a degree other than 360 degrees. So an odd function is a function that has rotational symmetry of 180 degrees. That means that if you rotate this function 180 degrees about, let's call it about the origin. So if you rotate this function 180 degrees around the origin, you can even move your whole paper and take a look at what happens. If I just rotated 180 degrees, so flipped it upside down, it looks the exact same. It's going up on the left, going down on the right. If I put it back here, it's going up on the left and down on the right. So it's a function that has rotational symmetry of 180 degrees about the origin. The official definition is a function is odd if and only if f of negative x equals negative f of x. What that means is if you plug in negative x for all of your values that you have, what it will give you back is the fully negative counterpart to your original function. So your how-to guy is like, hey, if you have xy, then you definitely have negative x, negative y. So we can think about it visually here on the graph, that if we have, let's call this 4, 1, then that means that we would have a negative 4, negative 1 in our graph. So if you kind of think about it, comparing it like that way, that's what that means right there. Okay, so let's just first determine whether something is even or odd. We're going to look, we have our first two examples have a graph to go with it, so we can kind of visualize yes and y. And then our next parts don't have graphs with them, but you can always make a graph because you have a calculator there that can do it for you. Okay, we're going to determine, which really means to prove, which means you can't just say yes, it's even or yes, it's odd. You have to prove to me that it's odd. Whether each function is even, odd, or neither. So here's the original function. Here's the graph of the function. We can tell by the graph of the function that this is going to be, it's going to be odd. And if you're still struggling on like how to spot it, we're looking for end behaviors that are opposite. We're looking like for going through the origin. Normally, it doesn't have to be, but normally it does go through the origin. Actually, yeah, it does have to be. It has to be across the origin. So it'll go through the origin, and then having some sort of like waviness around the origin is kind of a very non-mathy way of thinking about it. But that's kind of the behaviors that you're looking for. Going through the origin, end behaviors that are opposite, and that sort of thing. So that's kind of a good way to visually be like, oh, I'm pretty sure that's odd. But if you want to double check it algebraically, we are going to try the algebraic way of proving whether something is even or odd. I went ahead and took this rule from up above in my little definition boxes up above, that I know that something is odd if for every xy there's a negative x, negative y. Which means I want to find out what is f of negative x. So I'm going to plug in negative x for every place that I see x. I want you to make sure that when you plug in negative x, please, 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 I know it seems like extra work, but I promise it's going to help. Put it in parentheses. Just put it in parentheses, because I know at least a few of you are going to forget how to deal with the negative aspect of plugging in negative x. Like I bet maybe some of you put in minus x here as opposed to what it's supposed to be, plus x, because you're subtracting a negative. So you can see how like things can get really confusing really quickly, and putting in parentheses at first to kind of indicate like, hey, this is a puzzle piece that I've kind of substituted in here, helps you to visually be held accountable for what's happening in the equation. Negative x cubed, x cubed is x, and then negative 1 cubed, which is all that negative x is negative 1x. Negative 1 cubed, negative 1 times negative 1 is positive 1 times negative 1 is negative 1. So it becomes still negative. So that means it's negative 2x cubed plus x. And we're like, okay, all right, there's like some things that are similar, but it seems like maybe a few things are flipped. The sign for this first guy is flipped and the sign for the second guy is flipped. Maybe if we take a look at what is negative f of x and realize that also in your definitions above, we wrote f of negative x equals negative f of x. So if you can prove that this expression is going to be equal to this expression, then you can prove that it's odd. So negative f of x means that I take my original f of x, I put parentheses around it, please put parentheses around it, and I put a negative in front. The reason why I want to put parentheses around the whole thing is because I need to realize that I'm distributing that negative to the first term, but also to the second term. I guarantee you some of you are going to make that mistake. Don't be that student, okay? Go ahead and put parentheses where you need to put parentheses to be held accountable. These negatives are going to trip you up. Don't let it happen. Okay, so I'm going to go ahead and simplify this. This is negative 2x cubed plus x. Since these guys are the exact same, I can say f of negative x equals negative f of x. The function is odd. So just saying that the function is odd is not correct for these types of problems. It says that you need to prove it, which means that you need to show me what happens when you plug in negative x for all of your x values. For all of these, even or odd, plugging in negative x is going to be your first step. So if you're somebody who likes steps and lists and rules, write that out. Step 1, plug in negative x. That will be the same step for either an even or an odd function. So that's a good first step to write down. There aren't always steps with math, but sometimes we get lucky and there are. Okay, I want you to go ahead and take a look at